Have you ever wondered if lottery numbers are uniformly distributed, or if some numbers occur with greater frequency? How about if the types of movies people prefer are different across different age groups? What about if a coffee machine was dispensing approximately the same amount of coffee each time? You could answer these questions by conducting a hypothesis test, and the distribution you would use is a chi-square. At the core, each of these questions are about variation. For the chi-square distribution, the population mean mu is equal to the degrees of freedom, and the population standard deviation sigma is equal to 2 times the degrees of freedom. The distribution is asymmetrical, as you would guess, because it is a squared value and it cannot ever be negative. The distribution begins always at the origin. This will give us a bit of trouble in a minute as we learn to read the probability table. No longer can we be sloppy, knowing that the symmetrical distribution gives us a plus or minus number for both tails, like the normal and the student's t distributions. Like the student's t distribution, however, there is an infinite number of chi-square distributions, one for each degree of freedom. The distribution becomes less skewed as the number of degrees of freedom increases. This is something like the student's t distribution, but the chi-squared will always be tied at the origin, 0, 0. The decision rule for a hypothesis test using the chi-squared is the same as for all the tests we have done, or ever will do. Simply, if the calculated test statistic falls in the tail of the distribution, beyond the critical value, then we cannot accept the null hypothesis. If, on the other hand, the calculated test statistic falls in the zone between the critical values, we cannot reject the null hypothesis. This, of course, requires us to be able to look up the critical values. We see that the table looks similar to the student's t-table. Both have alpha values across the top and degrees of freedom down the side. There's one interesting difference. The alpha values across the top include the values 0.1, 0.05, 0.025, and 0.01 for the typical confidence levels. On the chi-squared table, however, the top also includes 0.99, 0.975, 0.95, and 0.90. These are because the chi-square is asymmetrical. For the student's t, we could use a single number for the critical value, whether or not it was on the right-hand side of the distribution or on the left-hand side of the distribution. We cannot do that here. Again, drawing a graph of the distribution is helpful. Here we have the chi-square distribution for 20 degrees of freedom, and we are looking for the critical values for a test with 90% confidence. We mark the tails and shade in 1/2 alpha in each tail. To find the chi-squared critical value for the right-hand tail, we look up the chi-squared value in the table at 0.05 at 20 degrees of freedom. This is exactly how we found the appropriate value from the student's t-table. We find the value of 31.410 and mark it. Please note, this is a chi-squared value, and it is not a number of standard deviations like we've been working with before. 31 standard deviations is an absurd number and should tip us off that this is something very different. A chi-squared value is simply for setting the critical values and will not give us any reference back to the normal table probabilities. To find the critical value for the left-hand tail, we have to go back to the table. The table is set up to be read from right to left, so we want to find the column with 0.95. This is the amount of probability in the right-hand part of the distribution, so that 0.05 probability is left over in the left-hand tail. Going down to 20 degrees of freedom, we find that the critical value for the left-hand tail is 10.851. Here again, the graph helps us keep track of all these things. Chi-squared tests can be both two-tailed tests and one-tailed tests, so graphing the problem will sort out which column to look for to get to the critical value. And now, to use our newfound knowledge, the test of a hypothesis of a population variance.